Turning the camera on, we're looking at questions on the homework. You said number 37? 47. Okay, let's look at number 47. Just making a video today for, there's a few people absent, so I'm going to be posting videos today and tomorrow. Number 47, we're looking for f prime. And so 1/4 is a scalar multiple. Think of this as blob squared, where the blob is sine 2 theta. And so the narrative that runs through your mind is the derivative of blob squared is 2 blob to the first times the derivative of the blob. Well, the blob is sine 2 theta, so now start over again. The derivative of sine blob is cosine blob times the derivative of the blob d theta d theta. When you simplify, it comes out to 1/2 sine 4 theta. Why? Because remember, there is a double angle identity in trig that says 2 sine blob cosine blob is sine of 2 blob. Now, it may not seem obvious that we can use that because it's like, wait, how can I use the fact that sine of 2 theta is 2 sine theta cosine theta when there isn't a 2? Well, if there isn't a 2, you can put in a 2 and counterbalance with the 1/2. We're motivated to use sine double angle. So we put in a 2 and counterbalance it with the 1/2. That's why the sine of 2 theta formula is why we're permitted to apply it here. Does that answer your question? That's probably the hardest part of this, was using sine double angle in the case where it doesn't seem to quite fit. Further questions on the homework due today? Number 47. Yeah, Graham.
So on 47, you got cosine just because it is the derivative of sine. That's what you
Yeah, the derivative of, again, the 1/4 just tags along for the right. It's a scalar multiple. The derivative of blob squared is 2 blob to the first times the derivative of the blob. The cosine 2 theta came in because it's the derivative of the blob. Further questions? Yes.
So you did like the double angle for the sine 2
Yeah.
theta, but why don't you do the double angle for the cosine?
Well, I would use double angle for cosine 2 theta if the problem that I'm looking at is something like, for example, if I had cosine squared of 5 beta minus sine squared of 5 beta, then I would use cosine double angle to simplify that. That's just cosine of 2 times 5 beta. Because the cosine of a double angle, there's 3 versions of it. Cosine, cosine, and sine, sine. There's cosine squared of blob minus sine squared blob. That's one of the versions. There's a couple others. But when I'm looking at what we have here, what we were dealing with on problem 47 matched up with, it was super close to the fact that sine of 2 theta is 2 sine theta cosine theta, but instead of theta we're using blob. The sine of 2 blob is 2 sine blob cosine blob. Which, this is super close to it. The only thing that causes this to depart from what we want is a number 2. Well, we can put in a number 2. It's called doctor and counterbalance. I doctor up the problem by multiplying by 2. I counterbalance by multiplying by 1/2. Further questions? Yeah, Ethan.
So wait, what's the formula you used to get from
Here to there?
No, next one.
From here to there?
Yeah.
I used the fact that sine of a double angle is 2 sine theta cosine theta.
Yeah.
Sine double angle. Further questions on the homework due today?
No, wait, no, wait. Oh, wait. Oh, okay, I see it now, I see it.
Great. Yeah.
So
go
you're
ahead.
saying
Will.
instead of it being a theta, it's a blob. So it's
Yeah, it is true
you're saying
that
instead
the
of sine
sine
it's sine
of
blob.
2 smiley face, the sine of 2 smiley face would be 2 sine of smiley face
So if smiley
cosine of
face
smiley face.
is 2
Yes,
is
yes.
2 theta, then
That's
you
right.
can do that.
Further questions on the homework due today? Now, today's lesson is high stakes. It had, when I planned this out, I was thinking today would be a block day, but it's not. So we're, oh yeah, you can go ahead.
One more. Number 77.
Yeah.
We never went over what tangent squared derivative was, so.
Right, but you don't need that because all you have to do is think of it as blob squared. We did go over the derivative of tangent. So think of this as blob squared. The derivative of blob squared is 2 blob to the first times the derivative of the blob. And since we went over the derivative of tangent and secant squared, we can use the chain rule to do this problem.
Oh, okay, I see now. Okay.
So let's jump into our lesson on implicit differentiation. And this is going to move at about a 25% faster pace than you're accustomed to. It's going to be a fast-moving lesson, but not unbearable. The homework on implicit differentiation is due tomorrow. The solutions are online. And since the test is 1 week from today, I also have the problem set available to hand out to you before you go. In fact, I'll just let you know that it's right here. I'm going to ask that you pick it up on your way out of the room, or just go and pick it up before you pack up. The problem set is aim to do that for the day before block day. So, but again, please don't get it now, but you can get it later. All right, implicit differentiation. For your handout for implicit differentiation, first page is review. And we're not going to take the time, since it's not block day, we're not going to take the time in class to do this review. But I do want to alert you to the fact that these items down here, we're not really going to hit them until Unit 5. So the review that I would encourage you to consider is just this section here, but you have to do that outside of class. Let's move into our first page. So go to the second page of the handout, where it asks you to find the derivative of secant y with respect to y squared. Might feel like a slap in the face. It's like, wait, I found the derivative of things with respect to x. I found the derivative of things with respect to y. We've even found the derivative of things with respect to t when we were trying to find dr dt, the rate at which the pelican should be moving. We've never had to find the derivative of something with respect to y squared. What's going on with that? You might legitimately be wondering. Well, first of all, it's not as bad as it looks, as long as you're willing to do this. Let's just make a substitution to make this less of a headache. Let's let u equal secant of y, and let's let v equal y squared. So now we can reframe this problem as finding the derivative of u with respect to v. du dv. They're really just asking us to find du dv. When a problem looks like it's a bit of a headache, you can reduce the headache-inducing properties of the problem by just putting letters in for the things that look complicated. And now we see that this really is an opportunity to use the second version of the chain rule. To find du dv, instead, we can find the first link in the chain is going to be du d what?
Why?
Yeah, since u is related to y, we're going to find du dy. And then since that's a dy, we have to make this a dy upstairs, and dy dv would be the second link in the chain. So, what started out as a highly mysterious problem has now been reframed so that we're in the familiar territory of the chain rule. Turns out that the chain rule is a big part of today's lesson, which is implicit differentiation. What we're looking at here is really just review. It's not the new material yet, it's review. So, see if you can finish it up from here. Now that we've reframed the problem as a chain with two links, please try to find both links of the chain on your own. I want to jump in here with a little bit of commentary. Du dy is pretty straightforward. Just think of y as a blob, the derivative of the secant blob, tangent blob times the derivative of the blob with respect to y. But finding dy dv, I would recommend that instead of solving this equation for y, instead find dv dy, and then take the reciprocal of it, because our framing of the problem is calling for dy dv. We wish that it were calling for dv dy, because it'd be a lot easier to find dy dv, or rather dv dy than dy dv. But we can just find dv dy, find the one that's easier to find, and then flip it. Here's how it goes. Yeah, they're calling for dy dv, but let's find its reciprocal dv dy because it's easier. dv dy, can someone tell me what dv dy would be based on this equation right here?
2y.
2y dy dy, which is 1. Okay, so did you know that if dv dy is 2y, that dy dv is 1 over 2y? Yes, it is that straightforward. So that means that the final answer to this problem, du dv, which I've run out of room here, so I'm going to put the answer up top. It's du dy, which simplifies to secant y tangent y, times dy dv, which we've discovered is 1 over 2y. Final answer to the warm-up question. Any questions on this problem right here? Yeah, Stephanie.
So when you said you took the reciprocal of
dv dy.
so you take the derivative would be with respect to y.
Just 2y. Yeah, and then I just flipped it. That's all I did. It's kind of nice. You can do that. Sometimes you get problems that are really mysterious looking, and it's just that you just need to realize that this is a possibility, and then it becomes straightforward. Okay, so orthogonal curves. By the way, orthogonal is kind of like the vector version of perpendicular. So when you see orthogonal, think perpendicular. And perpendicular in terms of calculus, two lines are perpendicular. That means their slopes are opposite reciprocals of each other. So if you have, just since it says to talk about this here, it's part of the lesson design. Suppose you have a blue curve here. Its tangent line is this red line. If the blue curve is orthogonal to the green curve at this point, then that means that the slope of the tangent line to the blue curve is the opposite reciprocal of the slope of the tangent line to this curve. So orthogonal, think perpendicular. So if the slope of this line is 1/3, the slope of the tangent line to the blue curve at this point of orthogonality is 1/3. What would the slope of the tangent line at that same point to the green curve be? Class? What? -3, yeah. So just that's a vocabulary issue. They'll come up in this lesson. When you see the word orthogonal, that means that the tangent lines are going to have slopes that are opposite reciprocals of each other. Okay, now to the topic of the day. All that was introduction. Now for implicit differentiation. Guess what? We've been doing differentiation a lot in this unit. It just means the process of taking the derivative. That's what differentiation is. It's always been explicit differentiation. Explicit differentiation is the name of the process that starts with solving an equation explicitly for one variable. So when we found dy dx equals 3x squared times dx dx, we were differentiating explicitly. Well, if you wanted to find dy dx down here in problem 1, good luck, even though luck does not exist as a causal entity. You're not going to be solving this equation for y explicitly. Yeah, it is implied, it's implicit that x and y are related to each other because they live in the same equation. But we're not going to solve this equation for y and then find dy dx. No. Yeah, we're going to be able to find dy dx implicitly. So there's no way to do implicit differentiation unless you know the chain rule. We're going to be using the word blob a lot today. Here we go. Since you know the chain rule, it's actually, I think it's going to be pretty straightforward. Y is a blob of x's. We don't even know what y is as a function of x. It's not like this equation up here where we can solve it for y, and we know that y is equal, the blob is x cubed. Here, y in the equation y equals x cubed, y is a blob of x's, and that blob is x cubed. Here, y is a blob of x's, but I don't know what y is. I don't know what the blob of x's is, but it's implied that there is a blob of x's that's equal to y because x and y live in the same equation. So when it's time to find, I basically contrasted implicit and explicit differentiation by the previous discussion. But now let's find dy dx. So it may look intimidating, but as long as you're willing to let the word blob flow through your mind, you'll be fine. Here we go. To implicitly find dy dx, we find the derivative of sine y, but think sine blob. The derivative of sine blob is cosine blob times the derivative of the blob, which we symbolize with y prime. By the way, y prime is what we're looking for. Okay. So the derivative of sine blob is cosine blob times the derivative of the blob plus. Okay, that's one part down. We've got, how many parts are there? 1, 2, 3, 4, 5, 6. There's like 6 parts to this problem. Because the derivative of a sum is the sum of the derivatives. We're going to have to take the derivative of each term individually. Okay, 1 down, 5 to go. Can someone tell me what the derivative of blob squared is?
2 blob. Times the derivative of the blob.
Yes, it's 2 blob times the derivative of the blob. It's 2 blob times the derivative of the blob. That's it. So that was part 2. 2 down, 4 to go. Okay? Now, honestly, part 3 is a product, right? So which rule are we going to have to use? We have to use the product rule.
Why make these so long?
Oh boy.
Here we go. So, part 1, done. Part 2 is done. Part 3 is derivative of the first times the second plus first times the derivative of the second. Okay. Oh, by the way, part 4 is going to be the derivative. Now, we are differentiating with respect to x. And when I write y prime, that's code language for dy dx. I'm differentiating with respect to x. So, how about we leave, let's leave part 3 just in skeletal form for now so we can get the big picture. Part 4 is 2x dx dx. 2x dx dx, which is just 1. You know what? It is so risky. As a teacher, this is risky. We're early on. I wrote y prime. I'm okay with you writing that down as long as you understand that it's really dy dx. I'll let you decide which one you want to write down. I just get nervous when I switch over to this more streamlined notation of y prime, when probably at this level of your development, I should be writing dy dx. Because dy dx is not 1. Dx dx is equal to 1. It's a big difference. Anyway, continuing on, derivative of 13 is 0, the derivative of sine 3 is 0. I mean, a constant, derivative of constant is 0. So, okay. So it's really just 5 parts. Part 1 is done, 2. Part 3 is not done yet. Would you please attach the flesh to the 4 bones here in the product rule? Try this unfinished part on your own. You may begin. It's this one right here. That's part 3. Put the derivative of part 3 right here. Be super careful with the chain rule. Russell, give you about 45 seconds. Just pause the camera until we come back on. We're back. Let's see how you did with the derivative of x to the 4th y with respect to x, thinking of x to the 4th as first, y as second. So here's the narrative that goes through my mind. Derivative of the first, 4x cubed dx dx, times the seconds, plus first is x to the 4th, times the derivative of the second, dy dx. Okay, now let's simplify. We're not done until we find the slope of the tangent line at the point A comma B. given that a comma b is on the graph of this relationship. Yeah, so let's simplify this. Here's where I think it's probably not a bad idea to replace the dy dx's with y prime plus 2y times y prime. Replace the dx dx's with 1 because the derivative of x with respect to x is 1. So plus 4x cubed y plus x to the fourth y prime plus 2x equals 0. So that's my first level of simplification. The dy dx's are y primes, which is what I have to solve for. Dx dx's are 1. Before we move on to the next line, do you have any questions as to what happened so far? Now the calculus is over. It's just a little bit of algebra 2. I'm going to factor y prime out of the 1, 2, 3 terms that contain y prime. When I factor y prime out of those terms, what's left in parentheses is cosine y plus 2y plus x to the fourth. Now the terms that don't contain y prime, would you please allow me to export those to the other side of the equation by subtraction, writing them as negative 4x cubed y minus 2x. Just doing a little bit of algebra. So I'm almost there. To solve for y prime, all that remains is to divide both sides by this trinomial. Final answer is y prime equals negative 4x cubed y minus 2x. And I'm seeing that that's not on the camera, so I'm just going to shorten this up a little bit. Minus 2x. Okay, so the numerator is negative 4x cubed y minus 2x. The denominator is this trinomial, which is cosine y plus 2y plus x to the fourth. Wow, we found dy dx without ever having taken the time to solve the original equation for y, which would have been impossible. Because of the sine function, there's no way to isolate y. So we're differentiating implicitly because explicit differentiation is mathematically not an option. So it's a good thing we have the chain rule and this concept of implicit differentiation. By the way, find the slope at the point a comma b. So here's the symbol that we use. We say y prime, big vertical bar, at evaluated at x comma y equals a comma b. So or, you know what, I could take, basically I'm going to evaluate it at, this is a more streamlined notation, at x equals a and at y equals b. So final answer, the slope of the tangent line is going to be negative 4 a cubed b minus 2a divided by cosine b plus 2b plus a to the fourth. That's the slope of the tangent line at the point a comma b, where a comma b is some point on the line. So that's a super complicated example that I like to start with because it's complicated enough for explicit differentiation to be impossible. Here, in problem 2, explicit differentiation is possible. We could solve this equation for y, but we're not going to because 1, it's faster to do implicit differentiation, and yeah, it's just faster. It's faster, and we're learning it. Question?
Yeah, where did the 13 plus sine 3 go?
I took the derivative of it. And 13 plus sine 3 is a constant, and constants don't change. Therefore, their derivatives are always 0. The derivative of c, that's why we always do that in the review. d dx of c is equal to 0. And if we had taken the time to do the review here in this lesson, we would have seen it right. It wasn't there. It's like we lost it from, it's been considered too basic to even review, but maybe we should put it back on page 1. The derivative with respect to x of a constant, like sine of 13 plus 3 or whatever, is always 0. Okay? So now you get to try one. Would you please draw a picture of what we're looking at here? I mean, you know from algebra 2 and from pre, this is a circle with radius 10. And 6 squared plus 8 squared is in fact 100. 36 plus 6 squared is 100. So there is a tangent line here at the point 6 comma 8. When you look at the picture, we're expecting the slope of the tangent line at 6 comma 8 to be a negative number. Would you please now use implicit differentiation to find the slope of the tangent line drawn to this circle at the point 6, comma 8. Give it a go. I'm going to hit pause and we'll come back in a minute. We're back. Hopefully you differentiated both sides with respect to x. All three terms differentiated with respect to x gives us 2x dx dx plus 2y dy dx equals 0. We're solving now for dy dx. By the way, let's divide both sides by 2. Dividing both sides by 2 and simplifying gives us x plus y times y prime equals 0. The 2's are gone. Dx dx is 1. Dy dx is y prime. So it looks as though y prime equals negative x divided by y. There's a formula for finding the slope of the tangent line drawn to any point on the circle. Now, we want to find y prime evaluated when x equals 6 and y equals 8. Therefore, the slope of the tangent line at the point 6 comma negative 8 is negative 6/8, which reduces to negative 3/4. We were hoping for a negative number. We obtained a negative number. It looks plausible that the slope of that tangent line would be 3/4. If they went further and asked you for the equation of the tangent line, you would say y minus 8 equals negative 3/4 times x minus 6. Any questions on problem 2? Today you're learning how to differentiate implicitly. It's a process called implicit differentiation. Let's go to page 3. Yes.
How do you know that it's with respect to x?
Well,
Why is it not?
because slope is change in y over change in x. It's rise over run. So you want to differentiate with respect to x. The variable with respect to which you're taking the derivative is always the denominator of the desired slope. It's rise over run. So if you want slope, you're going to be differentiating with respect to x. Thank you so much for asking that. Next page. Yeah, the way I see it, no question in calculus is really too basic, because there's, honestly, in calculus, this is a course where a lot of times students master Algebra 1. And then it's like, wow, now I understand that thing from Algebra 1 that was a little bit fuzzy back then. So here we go. Now we're changing it up. Instead of x and y, see, here it is. Good thing Stephanie asked that question, because now I want dt dw. It's like, oh, so are we going to differentiate? What are we going to differentiate with respect to? X? No. What will it be, class? W. Class, would you please differentiate this equation with respect to W? Do it implicitly. Don't take the time to solve for W. I mean, it could be done, but just differentiate implicitly. I'll work up here while you work there, and then when we're both done, we can look to see if we match. By the way, it is a product rule twice. I'm going to fold 5 into w squared. I'm just going to make this first, second. So we'll have an orange skeleton and a black skeleton. Differentiating with respect to W. Well, here's what I came up with. As I was differentiating with respect to W, I did derivative of the first times the second plus first times the derivative of the second to get 10w dw dw times t plus 5w squared times dt dw. That's a black skeleton. The orange skeleton product rule is 3t squared dt dw times w squared plus t cubed times 3w dw dw equals 0. We have to solve all that algebraically for dt dw. You've done the algebra. The calculus part of the problem is over. Although technically you do have to, calculus to find the derivative of w with respect to w. That's just 1. So we got 10wt plus 5w squared. Don't write t prime. At this point, seriously, let's just get in good mathematical habits. Just write dt dw. That's what we're solving for. Plus 3t squared dt dw, w squared, plus t cubed times 2w equals 0. So at this point, you can probably do it all in your head. The algebra here is not that big of a deal. dt dw is going to be every term that does not contain dt dw will be exported to the right-hand side of the equation. It will be negative 10wt minus 2t cubed w. The denominator will be the binomial that remains when dt dw is factored out of the terms that contain dt dw. Can someone tell me what is the binomial by which we will eventually divide both sides? What's the binomial that's left over once we factor out dt dw? Well,
5w squared plus 3t squared w squared.
yeah, and that's dt dw. So do we have to start over again to find dw dt? Oh, we're halfway done. No, we just flip it. If you don't have to start over to get dw dt. Woohoo! To find dw dt, you just flip dt dw to get 5w squared plus 3t squared w squared over negative 10wt minus 2t cubed w. Calculus is starting to move here, starting to flow. We're connecting together a lot of concepts. Any questions on example 3? Yes, go ahead, Dana.
Why is it like in the orange skeleton, the last term?
Yep.
Why is it dw?
dw? Well, I'm differentiating with respect to w. So as I'm dealing with this orange product rule, I'm thinking derivative of the first. Could think of it as t cubed is 3t squared dt dw. I'm differentiating with respect to w.
Okay.
Times w squared plus t cubed times, and then derivative of the second. The derivative of, you could think of egg squared. Derivative of egg squared is 2 egg to the first times the derivative of the egg with respect to w. Okay?
Thank you.
Yeah, you're welcome. So, number 4 falls into the category of practice. There's no new concept in number 4. So since this is not a block day, I want to skip up to number 5. Number 5 is a little more challenging. It says y is some angle between pi over 2 and pi. So I'm going to borrow some of our space for number 4, which we're skipping. And just in the context of unit circle, just want to remind you that y is some angle out here in quadrant 2 territory. They're asking us to, write the equation of the tangent line to the graph at x equals 1/5. Okay, there's a graph of sine y equals 4x. We're not going to attempt to sketch the graph of sine y equals 4x. We're just going to cut through the confusion using calculus. We're just going to get right down to the equation of the tangent line, which means I need to find dy dx. That'll give me the slope of the tangent line. Although, what's the point? Let's plan ahead. The slope will be dy dx evaluated at x equals 1/5 and y equals, boy, we better find out what y is because we're going to need that later. Let's just do that right now. Scratch work. Sine y equals 4 times 1/5 or 4/5. Okay. So sine y is 4/5. We need a muck diagram, MUC, muck, MUC, mini unit circle diagram. Y is an angle whose sine is 4/5. 4/5 is 0.8. So thinking back to unit 0, when I taught you muck diagrams this year, yeah, 0.5, 0.71, 0.87. So 0.8, there's 4/5 right there. Oh, so it looks like there's two angles. One of them is in quadrant 1. Here's one value of y. Clearly visible rim points. It's called a tangent point. Okay. Here's another candidate for y. But look, they're telling us that y has to be between pi over 2 and pi. So of the two that are in the muck diagram, we have to pick this one. Now, I just want you to know right now that this angle, the quadrant 1 angle, is the sine inverse of 4/5. I know that because the range of the sine inverse function, as you learned in advanced pre-calc or whatever pre-calc course you took, even if you didn't take advanced pre-calc, hopefully you learned that sine inverse has a range of values from negative 90 degrees to positive 90 degrees, or from negative pi over 2 to positive pi over 2. That's how I know the sine of 4/5 is this quadrant 1 angle, which looks like it's between 45 and 60 degrees. It's probably approximately 50 degrees. Sine inverse of 4/5 is about 50 degrees. What's this angle? The one they're asking for is not sine inverse of 4/5. Can someone use sine inverse of 4/5 to construct a representation of this quadrant 2 angle? Does anyone know what it is? By the way, if this were 50 degrees, what would that one be? 180 minus would be like 130. So it's pi minus this. So y is pi minus the sine inverse of 4/5. Okay, so in fact, we can even set up basically the equation of the tangent line. We know everything else except for the slope. It's y minus y1, or y minus the quantity pi minus the sine inverse of 4/5. It's y minus y1 equals m we don't know yet. M is, we're going to have to differentiate implicitly. So I'll leave a space for it times x minus 1/5. So we almost have the equation of the tangent line. All that we have to do now is use calculus. Most of the problem is pre-calculus. Now let's do the calculus. Class, would you please use implicit differentiation to differentiate both sides of this equation with respect to x? Right over to run. Change in y over change in x. Differentiate with respect to x. When you're done, look up here, see if we agree. Okay, I'm done. So when you're done, you can look up here. I came up with 4 over cosine y. That's what I have for the formula. And, oh, this is interesting. Cosine y. So it doesn't matter what x is. When I'm evaluating, all I need is cosine y. Oh, no way. 3, 4, 5. We can use our 3, 4, 5 triangle knowledge. Imagine that we, instead of a unit circle, suppose we take a circle of radius 5 instead of radius 1. Right? The sine of y is 4/5, which means the cosine of y has to be what?
3/5.
3/5. It's 4 over 3/5. 4 over the cosine of y has to be, wait, oh, except we're in quadrant 2. Negative 3/5. So, negative 20/3 is the slope. Wow. What an amazing review of the unit circle and muck diagrams. Wow. Wow. There's so much wrapped into that problem. So, yeah, Marcus, go ahead.
How did you get from cosine y
To negative 3/5?
Yeah.
You know what? Let me just expand this out a little bit here. So, in the unit circle, I mean, the unit circle, the word unit means 1, and circle of radius 1. We've already decided that the sine of y is 4/5. So you could say that this side is 4/5. Think of 1 as 5/5, okay?
Wait, how do we decide if the sine was 4/5?
Well, the sine of y is 4 times x.
Oh, yeah.
And x is 1/5, okay? So the sine, so think of, instead of the unit circle, think of it as 5/5. You've heard of a 3, 4, 5 triangle. Think of a 3/5, 4/5, 5/5 triangle. We're just using the 3, 4, 5 Pythagorean triple to pull this off. That's all we're doing. We're using geometry of all things. Instead of a 3, 4, 5 triangle, I want to hear that from the surgeon. Instead of a 3, 4, 5 triangle, 3, 4, 5 right triangle, we've got a 3/5, 4/5, 5/5 right triangle. Okay? So, if the sine of y is 4/5, which is true for this angle and that angle, then we've got to be over here. So if it were a quadrant 1 angle, if this had said from 0 to pi over 2, we would have said that the cosine of y is positive 3/5. But since we're in quadrant 2, we have to say the cosine of y is negative 3/5. Okay? So a lot of great review in there. Trig review. Let's go on to the next page. Woo! Wow. And it looks like, yeah. So, yeah, second derivative. Second derivative, that's not a new concept, class. I want to do one example in the 30 seconds that remain. So I'm going to lead you through this one because we don't have time for you to try it on your own. It's going to be 2x dx dx. Just find the derivative plus product rule skeleton equals 0. So derivative of the first times the second plus first times the derivative of the second is dy dx. So simplifying things gives me 2x plus y plus xy prime equals 0. Doing the algebra, solving for y prime gives me negative 2x minus y. It's got to all be divided by x. So that's y prime. Class, to find y double prime.
Jonathan Chen, Vince Araneta, Simon Shackelford.
Okay, welcome back. For those of you who didn't, I'm finishing this problem now because we didn't have time to finish it in class. They're asking for y double prime. And we've made it halfway through. We found y single prime. So now I'm going to take the work that we've done so far and shorten it up. And I'm just going to put forefront here what it is we've discovered. The halfway point is y prime is negative 2x minus y divided by y. To find y double prime, I'm going to set up the quotient rule skeleton of low d high minus high d low, draw the line square below, so the denominator will be y squared. There is a nuance here that's a little unexpected. So when I'm doing low, that's y. D high is where the surprise is. I'm differentiating with respect to x. D high is going to be negative 2 minus y prime, because the derivative of y is y prime, so it's low d high minus high is negative 2x minus y. D low is also y prime. Well, guess what I'm going to replace the y primes with?
Oh.
This. So to get y double prime, the final answer is negative 2 minus the y prime thing, which is negative 2x minus y over y, minus,
Students, we have lots of college reps here today. We have reps from Bethel College, Indiana, Dordt College, Messiah College, Samford University, and Taylor University. The reps are available to speak to in the atrium.
So notice both of my y primes got replaced with negative 2x minus y over y. This is really small over here. There's probably no way you can see it on the camera. But I will say it. The final answer is y times the quantity negative 2 minus the quantity negative 2x minus y over y closed quantity minus the quantity negative 2x minus y closed quantity times the y prime again, which is negative 2x minus y all over y, and the whole thing's over y squared. So that completes the lesson. Homework due on Friday. We'll see you then.